Well, good morning and good afternoon. Welcome in from across the continent for another Exploring by the Seat of Your Pants broadcast. For those joining us for the first time, we're all about bringing conservation, adventure, and science into classrooms around the world. And you are catching us on a very special day. You are catching us on our second of two amazing virtual roundtables with the 2025 laureates for the Gairdner Foundation. So for years now, we've partnered with the Gairdner Foundation to showcase and celebrate their laureates, some of the most accomplished and amazing biomedical and health researchers on planet Earth. Back on September 19th, we did our first program with them. I really encourage you to check it out. Bit of an unwieldy URL there to bring up live, but it is on our YouTube channel and the Gairdner YouTube channels alike. We featured 5 incredible scientists, and it was a wide-ranging discussion on all manner of incredible innovations in the world of medicine and, again, biomedical health. Today, we are keeping the excitement going with 3 more amazing laureates. Mike, who just arrived, is wrapping out our trio of incredible scientists today. So I'm going to begin by welcoming in all 3 of our laureates, and then we're going to dive underway with a few videos highlighting their work, some questions, and then we'll be looking to you in the chat for even more queries as the program goes along. So without further ado, Paul, Spiros, Mike, welcome to the broadcast. It's so nice to have you gentlemen on today, and welcome to Gairdner. I am going to put you all back in the background because I have all the power, and I'm going to begin with a nice video highlighting Spiros' amazing work before we dive in with questions for him. So without further ado, here we go.
I'm Spiros Artavanis Tsakonas, and I'm a developmental geneticist. I work at Harvard. So I have been working on NOTCH for the last 40 years. NOTCH is a communication pathway that allows cells to communicate. Whether you're a fly or a human, you start from one egg, one cell. This cell proliferates and it starts building an organism. So I decide to become one thing, and my next door neighbor takes that into account, and it does something that is the consequence of my deciding one thing. So the signaling framework that allows cells to communicate is remarkably conserved across evolution, all right? Something that we have been working on is to see how NOTCH activity is integrated with other cellular functions. The signaling pathways must coordinate their action and integrate their action so that the biological outcome is the correct one. I have been
Spiros, I'm bringing you in before we dive in with our question. And one of the first things that jumps to mind for me, I've got to say, is that you're just glowing in that video. And I think as a boy growing up in science, I thought of science as this distant thing a little bit. You know, I am a scientist by background, but I think in school we come to think of it as very serious, and it's serious people doing serious things in serious labs. And my thing in this Gairdner series has been that people are just absolutely delighted in the work they do. So thank you for being so passionate just in the video. Again, when I did my undergraduate in biology, we had fruit flies, we had C. elegans, we had Arabidopsis, we had all these model organisms, and scientists would do work on them, and we'd translate that into things for human health. And that's a concept that's sort of hard to get across to an everyday audience. So I'm curious how you bridge that gap. If you're trying to explain to people that work on a fruit fly and the genetics on it can fundamentally change how we help people, how do you bridge that gap?
Well, whether I can bridge the gap or not, you will be the judge. But one of the biggest lessons in biology in the last 30 years, more, is conservation of basic mechanisms. It is quite clear that the basic biological mechanisms that guide cellular physiology are conserved, actually, from flies to worms to humans. There's no doubt, of course, that we are not, we have the different physiology than flies. However, the underlying biochemical mechanisms are very much conserved. So in disease, the best way to address disease is by understanding the mechanism underlying a particular ailment. And you have, if you have a mechanism that you can analyze in model organisms, then that allows you to apply that, if nothing else, as a question to higher organisms, including ourselves.
It's a beautiful answer. And as a boy, I was obsessed with Charles Darwin, and there's a lot to love about natural selection. But I think the biggest is that it's the idea that, you look at a tree and you're related to that tree, and you're related to the worm, and you're related to the fruit fly that's been buzzing around and annoying me in my room all day. And the insights that you can glean from that are just really, really special. So I love that as an answer. Thank you so much. Oh, Spiros, we are going to be coming back to you with many more questions in the rest of our broadcast, but thank you for our kickoff query. We are going to dive right in with a second video highlighting the work of our other two laureates today, and then we are going to put the screws to them in some extra questions. So here we go.
I'm Michael Welsh. I'm at the University of Iowa, and I'm a physician scientist. Most of my research and the research that this award is for focuses on cystic fibrosis. The major cause of morbidity, suffering, and mortality is lung disease. My research began to focus on how the lung controls the little bit of liquid that's inside the airway. What goes wrong? Why does this person have lung disease? The first thing was, can we just take that gene that's defective, put a normal copy of that gene back into a cystic fibrosis cell and make it work more normally? It forms a pore, sort of like a little channel, a little tiny pipe that sits in the cell membrane and lets chloride flow back and forth through it. You have a defect in the gene, so it's giving instructions to build something, but it's giving the wrong instructions. So we did a really, really simple experiment. We made the cells, but after we made them, we just cooled them down. We just lowered the temperature, and it got to where it was supposed to be, and it opened. We were so excited because if we could do it in the lab, maybe you could do it with the drug. And Paul Niglescu, my co-recipient of this award, they did some fantastic work to develop a drug.
My name is Paul Niglescu, and I am a Senior Vice President of Research at Vertex Pharmaceuticals. Our work in cystic fibrosis goes back over 25 years, where we've been conducting research to discover small molecules, which are tablets or pills, that a patient could take to restore the function of the defective protein that causes cystic fibrosis. For many years, the ability to restore the function of a protein that was caused by a genetic defect was believed to be impossible. Where we are right now is with medications that can treat about 90% of people with CF.
There we go. See, someone had to be muted at some point during the broadcast. Otherwise, it was no fun, and better that it's me than you gentlemen. Paul and Mike, I'm going to bring you both in. The fact that we can have something that has that sort of efficacy is just unbelievable. And so I'm curious, Paul, it's sort of the big question in medicine. It's the big question in biomedical health. How do you balance the need for long-term research and dragging this out over many, many years with patient needs right now? So many people are suffering with this in the here and now, and you're working on something that might take 10, 20 years to develop fully. How do you balance all that?
Well, I think the way we approached the cystic fibrosis problem was with the end in mind, right? And that was, let's fix the broken protein. Let's fix that protein that Mike had done research on and showed that actually it is fixable with that low temperature experiment. And we just worked ourselves backwards from that. If that was the goal, we just said, what are the steps to get there? And I think sometimes what happens, at least in some of the biopharmaceutical research, is there is the temptation to take shortcuts. There is a temptation to just work on the nearest, easiest problem to solve. But I think if you turn it around and say, what's the end goal in mind, you can bridge from the near to the long term. And that's what we did. And it's a very rewarding process to be able to go through that.
I certainly bet it is. Thank you so much, Paul. Mike, you're back. And I want to lead in on this, the working with patients directly. So when I learned about cystic fibrosis and sort of different approaches to treating it, it came from this book. This is Atul Gawande's Better. It's one of my favorite books in the world of medicine of all time. And they highlight different hospitals' approaches to treating this, again, very common and very challenging disease across the United States, and how those hospitals have different sort of levels of efficacy. So I'm curious, as someone who's worked directly with patient communities, how does that inform the research that you do?
Well, it informs it a lot. I like to bring people with cystic fibrosis into the lab so that my postdocs, my students can meet them, can find out about what their disease is like. I had that experience myself. My first person with cystic fibrosis I met was a 7 or 8-year-old girl when I was a junior medical student. That was stuck in my memory. From there, I proceeded onto a curiosity-driven pathway. I just wanted to understand how parts of the lung work, how liquid, salt and water move back and forth into the airway, into the lumen of the airway, the inside of the trachea and bronchi, and what controls that. And then with time, as I became a faculty member, I was taking care of people with cystic fibrosis on the ward. And I thought maybe by studying this problem in people with CF, maybe by understanding something, maybe that could help people with cystic fibrosis. And it wasn't at that time more profound than that. It started there, and it just kept going.
Yep. What an impactful experience. And I mean, it's about as profound as it gets to have someone who's 7 or 8 who's dealing with a disease that might end their life prematurely. And it sort of underscores why you've won the Gairdner Award. It underscores why we were doing a broadcast like this, to feature the science from all 3 of you gentlemen. And so thank you very much to all of you for our first question so far. I'm excited over the next half hour to have a little bit more of a chat. And so we'll dive in with one for all 3 of you. And Spiros, you can begin with this, which is, what is the most exciting question in research that you'd like to see solved? And this could be, it's a big question, and it's one that you can stick with your own lane. It can be something entirely different. I'm just really curious to hear from all of you. So Spiros, we'll begin with you, and we'll go in order like we did before.
Well, for me, the most important question, and this is something that we still work on, is how do signals in the cell integrate with other cellular elements? As I said in the beginning, you have a particular signaling pathway, and this signaling pathway, in order to guide the appropriate cellular physiology, it has to integrate itself with other elements. Now, this is an old problem, and we knew that it existed from the beginning. However, only now, with all the omics approaches and the spectacular work with artificial intelligence and the AlphaFold and its derivative, can be addressed now, which is a new thing. It could only be addressed as of 2-3 years ago, not before that.
Yep. I love that you mentioned AlphaFold. I'm going to do a special plug for any in our audience that might not be aware of this as a technology. It won the Nobel Prize not too long ago and just completely has revolutionized medicine. Whenever we feature anyone talking about proteins in any way, they reference AlphaFold with awe, and for very good reason. Spiros, a great start. Paul, the most pressing question in research. No pressure.
Can I do 2?
You can. Go for it.
So one would be, if learning from the CF experience, if we could understand the cause of more human diseases. If we think about it, there are thousands of human diseases, and we actually don't know the cause of many of them. And as a result, our medications that we try are kind of trial and error. It's hit and miss. So to me, a big question is, can we be more precise in our treatment of human disease. The second one that I think I'd like to see if we could tackle would be, can we accelerate the design of drug process? You mentioned AlphaFold. You know, the promise of that technology is that we can visualize any protein, and the next step would be, can we visualize a medicine that could bind to a location in that protein? Can we design that in silico in the computer and just make it the first time, so we don't have to go through the 20-year process that we did to find the CF meds?
Out of curiosity, as a quick follow-up on this, is there an example of us starting to do that really well? Would like Operation Warp Speed be an example where we came up with a COVID vaccine in a pretty protracted timeline with all the safeguards in place, or are there other examples you can speak to?
Well, genetic therapies are a really interesting example. The RNA vaccine was actually designed in a weekend for COVID. And that was because they knew exactly the sequence that they wanted to target for the vaccine. And it was RNA, so it could be designed very quickly. I think the promise of genetic medicines, such as RNA or DNA, do offer the hope for this precision. But what we need to do is figure out how to get those RNAs and DNAs to the affected tissues. In the case of a vaccine, we just had to put it in the arm, and the arm muscle made the sequence for the vaccine. So I think there's hints that we can do it much faster, and the COVID vaccine is actually a very interesting example of that.
Yeah, it's such an interesting time to be alive. I mean, it doesn't really make the news in a broad and big way, and that's unfortunate, because it's an age of miracles in science and technology. Like, there's so many developments that are happening so quickly, especially in the last few years, that provide so much hope for millions, if not billions of people. That's fantastic. Thank you, Paul, very much. Now, going with our train, Spiro's got one question, Paul got two. Mike, by definition, you are allowed 3 separate research questions. That's how this works. But if you have a key thing you'd like to share with us, go for it.
Well, this one, I'm just going to stick with one. And this is a simple one. The most important question is the one you're interested in. And that's the one you'll work the hardest on. That's the one you'll be the most curious about. That's the one where you'll make mistakes and advances and go forward. And an example of that, Paul gave one example, how understanding the SARS or the COVID viruses and work before that laid the groundwork so that we could go very fast. In our work, in the work that Paul and I did, we used tools that people had discovered because they were interested in some problem. They weren't thinking about cystic fibrosis. So we used an electrophysiological tool. It's called the Ussing procedure, Ussing chamber. This is a tool that Hans Ussing invented because he just wanted to understand, how can the frog live in the pond? The pond's got fresh water. The inside of the frog is salty, saline. How can it maintain that salt gradient? How can it absorb it? We use tools, a patch clamp technique. This wasn't invented for cystic fibrosis. It was invented by scientists who are just curious. I wonder how ion channels can work in a neuron, in a slug neuron. They developed these tools. We build on those. This is a foundation. So you work on the problem that you're the most interested in, the one you think is the most important and the one that you're interested in. And you may go forward, you may be laying the groundwork, or you may be diving deep towards a specific disease like cystic fibrosis. But you'll go the furthest and work the hardest and have the greatest insights with what you're interested in.
Mike, it's a beautiful answer. Newton, who's probably the most iconic genius in the history of science, talked about standing on the shoulders of giants and the work that he did. And so fundamental research has been something that's been the undercurrent of the entire Gairdner series with all 8 of our laureates. And welcome back, gentlemen. So I really appreciate that as an answer. I'm sure we're going to be coming to that over the next few questions as well. We are going to dive in with some of our questions from our students now. So we were pleased to partner with the amazing folks at Visions of Science. For those who don't know, Visions of Science is based in Toronto, does incredible work to give underserved students more opportunities in science and engagement. And so we're going to dive in with a few quick questions from them, and then we'll take some from our YouTube audience as well. And they're already pouring in there, which is fantastic. So Tariq has our first question. We're going to play this, and we'll do reverse order. Mike, you get to be first this time.
My name is Tariq, and I just have two questions for you. What do you think the field of your research will look like in 20 years? And if you can give your younger self advice, what would it be?
What would your research field look like in 20 years? And if you were to give your younger self advice, no pressure at all, Mike.
I'm not any good at predicting the future.
None of us are. That's fair.
I'm just enjoying the ride for right now. What advice would I give to my younger self? That's a good question. I think I would give myself two pieces of advice. One is to stay a bit naive. So when I grew up, I didn't have an iPhone, right? They didn't have email, the social media and that. And that actually was good because and I grew up in rural Iowa. So I didn't have a lot of expectations. People weren't putting expectations on me for what I might do, what I might not do, what's the best thing to do. I got to just sort of decide it by myself. I didn't have to have expectations because I was looking at my iPhone and looking at social media. And I think that's really important because you want to live your life towards your own goals and the goals that you discover over time. I think the other thing I would tell myself and other people is go all in. If you're going to try something out, go all in. Don't go halfway. If you go all in and you find out, no, this one's not for me, I'm going to go a different way, you'll be confident in it. You won't have the excuse, well, I don't know, I didn't really try. Go all in. And here, again, I had the advantage. We didn't have iPhones then. So I could focus totally on the problem I was looking at. I could try something out, give it my full attention, not be distracted, go all in. Those would be the two things that I would suggest. Live to your own expectations and go all in.
Fantastic piece of advice, Mike. I went to the University of Toronto for an undergraduate in biology, and our first year class was 2,000 students. And I could tell you 90% of those students were like, I'm going to be a doctor. And after first year, about 90% of those said, oh no, I'm not going to be a doctor. What am I going to be? And so 10 years removed from university, I'm in this position where I get to talk to upcoming students that are going to their first year of university. They're 18 years old. And my piece of advice is the same. It's just enjoy it. Have fun. See what piques your interest, because you have no idea going in when you're 17 or 18 years old what's ultimately going to be your career. I think that's a beautiful piece of advice. And thank you so much. Jeez. Spiros, we're going to mix up the order because I have all the power, and I'm coming to you next. Come on in.
Well, I have a very, very simple advice to younger people. One is that they should not be afraid to make mistakes. If you don't make mistakes, you don't learn. And the second thing is that you should not feel embarrassed to follow your intuition. In science, passion is essential. And so I think that students must have fun, intellectual fun, and they should follow their gut.
That's beautiful. And I love that you highlighted failure. We had this a lot in our first Laureate talk as well. Every scientist that we feature on this broadcast, both within Gairdner and without, fails all the time, was terrible at most things that they ever tried, and just persevered at it and ended up having an extraordinary career. So I think there's very little better advice than that. And I'm really glad that we snuck that in. Thank you, Spiros. Paul, you're up. Our finale. It's hard being the third person to offer advice because it might be similar, but try and blow us away. No pressure.
Well, I'm going to start with the first question, which is, what does science maybe look like in 20 years? And the question made me think, how far have we come in the last 20 to help kind of see where the next 20 might be? And just something for your audience to think about. When the CF gene was first identified in 1989, it took a team of researchers about a year to find it. And they were building on previous technologies that had been developed before that. But it was a massive effort, Canadian and US scientists working together. Today, to discover that gene would probably take a few hours. So if we project forward and we think about the ability to do sequencing of genes, to measure genes that are expressed in each cell at a particular point in time, either in normal or diseased tissues. As we think about the ability to scale all this into smaller and smaller samples, because we have much more sensitive methods, I could imagine the entire discovery process for a drug occurring in something the size of my office. And when you think about just that pace of acceleration, I think the future is going to be so incredibly exciting, and so glad to be talking to some of the young people, because the potential is immense. And it's because technology is evolving so quickly. We didn't even talk about artificial intelligence and the ability to help use these sorts of tools to handle massive amounts of data. But at the end of the day, human curiosity and human drive will be the essential element for guiding all this technology in the right direction toward human health. In terms of advice, I just have one, because I'm very goal-oriented. And I think as I look back, I wish that I had enjoyed some of the steps along the way a little more. So celebrate the small victories, celebrate even the failures. As long as you learn from them, they're important.
Whenever my wife sends in poetry to be published, because it's a notoriously fickle industry, whenever she gets a rejection letter, we have a little party, because if you send in 100 things, maybe you get one succeed. But along the way, that process is really, really important. And the technology evolving, I mean, we've all seen this in computing. Mike, you talked about not having an iPhone when you grew up. I didn't have an iPhone when I grew up. I read encyclopedias as a boy, and I went through the dictionary to learn things. I mean, honestly. And so to see it go from that to everyone has a supercomputer in their pocket in 20 years is unbelievable. And we're seeing that pace of change in medicine right now. So it's, again, it's the golden age of wanting to be a scientist, wanting to be to understand the world around you. And you guys have given us some great pieces of advice. We're going to take one more from our Vision to Science students, and then we're getting a whole bunch of great ones from our Gairdner Awards chat. So I'm going to dive in there in a second, but let's bring up our second question, and we'll go from there. Here we go.
Hi, my name is Tariq, and I just have 2 questions.
There we go.
Hi, my name is Aisha. My question is, how do you stay motivated when research takes a long time?
So you guys have been at this for a while now. How do you keep motivated? Mike, I'm going to start with you.
Well, you know, you think about research, you say, oh, this is hard work and long, but the previous speakers touched on this. It's exciting. I can't tell you how exciting it is to see something for the first time, to understand something for the first time. It just is the most exhilarating feeling. And so you have to then sometimes take small doses of that. You're working on a problem and you're pushing along. You have to celebrate, hey, we had an advance today, because you'll have many times when you go the other way. And Spiro's touched on this too. You can't be afraid of failure. And so you say, why are we going this way? Number one, because I love discovery. Number two, what we find out can maybe change the lives of people in a big way. That's been demonstrated in cystic fibrosis.
Yep. Mike, again, sorry, professional detachment out the window. Gairdner, you guys picked the best laureates ever this year. Way to go, 2025. These are spectacular answers. Spiros, I'm coming to you next. Take us away.
Your statement is debatable, but anyway. Thank you.
Anytime.
So
Spiros hit a button that kicked him out of the broadcast. This is also the joy of broadcasting, is you never know when this sort of thing is going to happen. So Paul, you're up. No pressure.
I think if we're not failing, we're not pushing ourselves. And what I used to tell our team when there would be a week or two or a month or even a couple of months where we just were hitting a wall, what I told them is, that's our job. Our job is to push through that. So you have to be excited about the goal. I think one thing that would keep me motivated, at least in the type of work that we do, and you mentioned it at the beginning, is at the end of the day, there's a human being that is hopefully going to benefit from your work. And if you just always remember that, and you meet these people. And I highly recommend for all of the students that if they're studying something, they go and they meet the people that the research is directed toward. You'll learn more about the disease, more about the condition, more about yourself by talking to people who you're directing your work towards. So just keep that in mind. You're trying to help someone. And what's more important than that?
I've been really touched this year in general, whether it's biomedicine, whether it's exploration, conservation, of the idea of centering people in the science and exploration that we do. It's something that I think all of us recognize maybe has taken a little bit of a back seat with the rise of social media, with the rise of digital connection, but there's nothing that beats being in person. And I love that that's your message. Thank you very much, Paul. Spiros, you're back.
I'm back.
I
don't know what
we had a good cry, and now you're good and you're in, and we are eager to hear your answer.
Well, again, I think that you work on a problem because you are interested in it, and every little step towards solving that problem is interesting. It may be challenging, but it keeps you going. I mean, I think that in science, if you don't have this tenacity to go ahead, even across failure, then science is not for you. Usually, in our experiments, 80% or 90% of the time, it's failure. Yet, if every success allows you to forget all the failures that happened before, then you're good for science. I keep on saying that to my students.
I'm sure they appreciate that, whether they're doing well or badly. You're going to fail. It's okay. And keep at it, and we'll see where it goes.
Exactly.
We've literally featured people that run departments in astronomy and math and exploring by the seat of your pants, and they failed it in university. Like, they flunked out, and then they went back and they tried it again. My brother-in-law is a space engineer that got 50s in math in high school, and he's come through that to where he is now. And so, guys, this is fantastic stuff. Spiros, I'm going to have you in the background for just a little bit, because we've got a question from our chat for Paul and Mike specifically, which is from our group at Garth Webb in Oakville. Thank you so much, our Marchetti class. They want to know, before the drug therapies were made, how is cystic fibrosis treated? How do we actually deal with this before we had some of the new technologies? And whoever wants to take this, you're free to go.
Well, Mike's the clinician, so he should start.
Yeah, so so when the first patient I saw was when I was a junior medical student, a long time ago. And I saw her, and she's having trouble breathing. She's coughing, bringing up foul sputum. I can smell what I learned was this odor of Pseudomonas. She could only talk in short sentences. And afterwards, when we talked with the faculty, I learned, she was 7 or 8 years old then. She was probably never, ever going to make it into the teens. And if she did, she wasn't going to make it out. Now, then physicians, scientists began to improve things. They began to treat more aggressively with antibiotics, trying to tamp down the infection in the lung. They used the ketchup bottle approach. Basically, the ketchup bottle, you pound on the bottom, we put on vests to percuss them, trying to shake that mucus loose out of their lung, trying to shake that infection out of their lung. We, for a while, had them in mist tents. We had them inhale saline. All those things helped. They all helped. But it was frustrating, because as a physician, I could work as hard as I could, and I couldn't touch the fundamental problem. And that's what's so exciting now. Now we can treat the fundamental problem. And it's just amazing. Now I see people with cystic fibrosis, and they're getting on with their lives. They're getting married. They're having kids. One of my colleague, Tony Fisher, came and talked to me about one of his patients who was running cross country competitively in the state cross country meet. And I thought, this can't be true. It cannot be true. It's so amazing, the lives. And I've been so fortunate to see that arc of discovery, starting with the patient, going through research and development and back to the patient.
The very first programs we ever had on for health here were a woman that helped people through heart disease and went on to take them on marathons and up mountains and these grand epic adventures that seemed so out of reach. And I think there's very few more hopeful stories than that. I think we can all recognize that drives forward our desire to do more work and our desire to invest in it than pretty much anything else. So I really appreciate that, Mike. Paul, is there anything to add? Great. And if not, there's a great follow-up question to this from one of our other audiences on YouTube.
Just real quick, what Mike described was moving from treating the symptoms of the disease, whether it was the infections or the thick mucus, to treating the cause. And the lesson, I think, in the CF story is if we can do that for more diseases, get to the cause, not just the symptoms, we will have better outcomes like we're seeing in CF.
Yeah. So this leads really nicely into a question for Spiros, and thank you very much for that, Paul. In the work that you do, this fundamental research, are we using this to help find causes of diseases? We've talked about this quite a bit today, is that there's so many things that we still don't know. At the most fundamental level, what has been your work to help us understand that?
Listen, let me just say that Paul and Mike's work is a perfect example of how basic science is translated into medicine and how basic science can save people at the end of the day. And because we have to always remember that basic science is the mother of invention. Without basic science, you cannot understand mechanism. And as Mike suggested, if you don't understand mechanism, you can't really cure things efficiently. You may stumble upon something, but these are not rational therapies. So I think that this is something which is extremely important. When we started working on Notch, there was a connection with cancer. But we know now that Notch is associated with a myriad of different physiological ailments, let's say. So when you start, you never know where you will end. And I have never been a big fan of focused research. I think focused research never works very well. It is the randomness and the freedom of research that will produce disruptive drugs and address very severe ailments.
We talked about this quite a bit in our first broadcast, and I think it's such an important point to drive home for anyone who is both entering into science and who's funding science on the governmental level, because we can be wrapped up in this idea that, oh, we're going to target something very, very specifically. CRISPR as a technology is the bacterial immune system. How do bacteria fight off infections? And look what we've been able to develop from that. You can do this with space science. Oh, the atmosphere of Venus looks a little odd. Oh, we've learned about chlorofluorocarbons here on Earth, and we've passed the Montreal Protocol. I mean, pick your science. The most fundamental, basic things that are driven by your own excitement, passion, everything else, as we've talked about with Paul and Mike.
And freedom.
Yes. Which is very important, more than ever today, perhaps. So you guys have been fantastic with all these answers. Thank you so much. Spiros, I'm going to begin with you with our final question from YouTube, and then we'll wrap up after that because time flies when you're having fun. One of our classes wanted to know about Health 3.0, which in short, the idea that instead of just trying to stop people dying at the very end of their life, we're trying to have a longer, healthier lifespan throughout the middle age, throughout old age. Can you speak to how we're trying to make this happen in fundamental research and the health field right now?
Well, I'm not an expert on aging issues. However, again, aging, you can actually consider aging as some kind of a disease, if you will. All right, it's not quite correct, but nevertheless, so. Understanding the mechanisms of aging is very important. I'm not a particular fan of huge longevity. I don't think that living 500 years is to the benefit of the individual or the society. However, to have a healthy life, and wealthy, I suppose, but healthy is the key word, is quite important. So if you look at what's happening now with all these neurodegenerative diseases that are affecting an aging population, and the aging population is aging because of the new drugs we have that keeps us alive much, much longer than they did in the 1930s, for example, or 40s or 50s. So I think that this is that's basically my answer.
I love that in direct contrast to the entire social media ecosystem of talking about health, you directly repudiated people living to 500 years old. Thank you very much, Spiros. I appreciate that so immensely. Mike, we'll come to you. Take it away.
I'm still laughing at Spiros. That's good, Spiros. I agree. I agree. We don't want to make. We don't want to even try to think about making people live 200 years or 500 years, whatever. But you want to live a healthy life. And in terms of aging, we have so many diseases that are associated with aging. The risk of cancer increases. Most cancers increase with aging. The risk of getting Alzheimer's disease or Parkinson's disease increase with aging. The risk of getting cardiovascular heart disease increases with aging. So we need to understand that, because what contributes to that? How do our genes contribute to that? Is it the environment? Is it what you've been exposed to? Is it the kind of work you do? Understanding those things, once we understand those, perhaps we can apply those to keep people healthy during their normal lifespan.
Mike, again, thank you so much. Paul, you talked about a few minutes ago the need to talk to people in your life, and it's so nice hearing from experts the same thing that I feel when I see all these articles and things hyping the opposite. So much appreciated. If I can walk the hill behind my house when I'm 80 years old, I'll be so happy, or maybe join one of those marathons or mountain climbing expeditions. But if you want to wrap us up with one final answer, go for it.
Sure. Well, I think two things need to happen, at least two things to address your question. One is earlier diagnosis of disease. In Parkinson's, for example, by the time someone is showing symptoms, 90% of the dopaminergic neurons are gone. So you can only do so much at that stage. So we definitely need earlier diagnosis. And then we also need the therapies that will specifically target whatever is going wrong. I've heard somewhere, someone told me, I don't know if it's true, but that at the end of the day, like there's only so much we can do to forestall the eventual decay of our bodily systems, and that ultimately everyone would get Parkinson's disease because those cells you're born with, and eventually they just run out of steam. But I think getting them to function longer and understanding perhaps when something's going wrong with them so that we can have that longer healthy part of life. There's great prospects for that.
Again, golden age of science and research. It's really, really exciting. I really encourage our classes, go beyond what you might see on social media, go beyond what you might see in short form media. Watch some of the Gairdner Laureates and their further talks and the stuff that we're going to be highlighting with them over the months to come. And I really, again, Gairdner.org, at Gairdner Awards. There's so much to explore and discover there. Gentlemen, this has been a fantastic roundtable. Before we wrap up, I know we've had all these long form answers. In the spirit of we are nearing the 45-minute mark, if you have one pithy, quick highlight of your work that you'd like to share with us before we say farewell to everybody. Paul, you're up. I'm going to start with you, and we'll wrap up with Mike because that's the order you're on screen.
Sure. Well, first of all, this has been great. I've really enjoyed the questions and listening to the other speakers and colleagues. I think I was reflecting on some of the comments from Spiros and Mike, and thinking about my own journey a little bit. And, I think as scientists, we have to ask ourselves, what part of the scientific process are we most suited for? Spiros clearly is thinking about the most basic foundational elements of research. And that's like the top of the funnel. That's any question is on the table. You can think as broad as you want, freedom, all of that. Then there's the part where once you know stuff, once you've learned stuff, what do you do with that? How do you apply it? And that sort of attracted me I was more interested in that focus, in that taking what we've learned and applying it to solve a problem. So I think as we think about all our journeys, we have to ask ourselves what part of that entire funnel most suits us.
Fantastic. Spiros, you were referenced directly. You're up.
Well, I think that Mike is absolutely correct. That is to say, it is the funnel that matters. Without the funnel, I mean, I will maybe at the top as he defined it, and he may be at the bottom, but we depend on each other. If we don't inform each other, it's all useless.
Yep. I love that we highlighted in our first broadcast too in the roundtable the idea that scientists, one of the great joys of becoming a scientist is that, we've got students in grade 5, grade 6 today. The thought of 7 more years of high school and then university degree and maybe 2 more university degrees on top of that, it's very daunting. But at the end of that, you end up getting to work with the most interesting people in the world, solving the problems that you love, collaborating internationally. And it's not for everyone, but if it is for you, I think all your answers today highlight how much passion and joy you can bring to science. And I think that's really important for our students here. So thank you for that, Spiros. Mike, you get to wrap up our show today. There you are. Take us away.
I have the best job in the world. I get to work on puzzles and the excitement of that. I get to work with young people, ask them questions, have them challenge me, influence the direction of their lives. I get to work with collaborators, which is great fun. The challenges that they point out in my own work or that we go back and forth with. I get to work on something that matters and work on a disease, but really work on contributing to that big groundwork, that big basis of knowledge that allows us to go forward for Parkinson's or cystic fibrosis or cancer, whatever. I can't imagine a better job.
If all of you are as adept as scientists and researchers as you are at conveying the magic and wonder of your work, you're all going to win the Nobel Prize, as many Gairdner laureates have in the past. And so I look forward to seeing the news items about that in the years to come. Gentlemen, thank you for your passion, your expertise, all of it. We really appreciate you taking part in the virtual roundtable. I hope your experience in the rest of all of Gairdner stuff is equally fantastic. And from me, thank you so much, and I wish you a wonderful rest of your day.